Our homes are fed with 2 huts but only 1 neutral that they share. And it might seem like magic that you can have almost 28 amps on this leg and almost 14 amps on that leg. But the neutral they share won't have the combine of those two. It'll have the difference between those two for 13.5 in this situation. So that's usually oversimplified and incorrectly taught as the current cancels. Current can't cancel. There's no current being canceled in that situation. That center tap carrying the imbalance is just Ohm's law. It has nothing to do with AC sine waves, the silly idea that something's 180 degrees out of phase with something else. This kind of shows that they can't be out of phase if it's going to work. But it is just Ohm's law from a center tap. Last year I built a panel where I stacked a bunch of D batteries, center tapped the D battery, and showed that that center tap off a stack of DC batteries will carry the imbalance. I'm going to draw it on the whiteboard and do it to my panel to show that what happens in real life pretty much matches what happens in the panel. On the drawings we're going to say 28 and 14. Over there things fluctuate a little bit, but it'll be the same idea. Let's go. Okay, so this is what we got. We have a transformer and the full length of the winding equals 240 volts. Half the winding is 120, the other half of the winding is 120. And then we have 2 hots, 1 neutral coming off that transformer. In this situation we plug in 1 hot plate and we get 14 amps. On this leg we have 2 hot plates for 28 amps. And then the difference between the two is 14 amps, and that's what returns on the neutral, which is what I tried to show in the beginning of the video, but real life fluctuates a little bit near 14, not actually 14. So what happens is, if we remove this neutral and lose that connection, we now have a 240 volt in series circuit with a 4 ohm resistor and an 8 ohm resistor. So you open the neutral, you convert it to a 240 volt in series circuit with 2 resistors. So in a series circuit, the current becomes constant, and you'd have 18 amps going through the entire circuit, 18.8. But this resistor would only see 160 volts, and this resistor would see 80 volts. Let's see if that's really what happens in the real panel. Okay, disconnected the neutral. Don't try this at home. And instead of 28 and 14, we now have 18.8 and 18.8 on both legs for voltage. So before we go to the real panel to measure voltage, I don't want to go hot to neutral because that'll still give us 120. I want to go hot to the area between the 2 loads that they meet, and hot to the area between the 2 loads that they meet, and that'll give me the voltage across each resistor or each load. Right now in real life, this is the neutral bar in the panel, not the neutral. That's disconnected. Okay, so I'm on the neutral bar. I get my meter set up. Here's one of my loads. If I go to that load for voltage, I get 161, and then the next breaker that's on, that's running the other 2 hot plates, I get 77, so just about the 80. All right, this is where the magic starts to happen, and I might start to lose people, but here we go. So if this is 160 volts and this is 120, there's a 40 volt difference. If this is 120 and this is 80, there's a 40 volt difference. All right, let's see if reality matches whiteboard and see if we can see that 40 volts. We're going from the neutral bar to the actual neutral, and we get 41 volts. There you go. So since there's a difference, if you make a connection there, current will flow back on the neutral. All right, so if I make that connection, I should get some current to flow at that connection. Those arcs were now the current deciding to flow on the neutral because of the 40 volt difference. So when there's an imbalance, current flows on the neutral. What happens if we removed the imbalance and made this a balanced load? So now when we balance a load, we unplug 1 hot plate, these ohms are equal to those ohms, which means in the 240 volt series circuit, they're going to split the voltage evenly. So now we'd have 14 amps going here, 14 amps coming back here, and 120 volts at each load. Let's see if that's what happens when I unplug one of the hot plates. So I have one of the hot plates unplugged, and now I'm at 14 amps and 14 amps. The neutral's still disconnected. So now with the neutral disconnected, from the common area between the 2 loads to the hot of each load, I end up with 120 volts, 120 volts. So now, what is the voltage difference from this to that and from this to that? It is 0. There is no voltage difference. So even if we were to add this connection back in, no current will flow on it because there's no difference in potential from this spot back to the transformer winding. For balance panel, what will the voltage reading be from the neutral bar to the neutral conductor itself? 0.2 volts. I'd call that 0 volts for the sake of trying to match the whiteboard. All right. Neutral reconnected. And I end up with about 14 amps. About 14 amps. And nothing on the neutral. The neutral is serving no purpose once we've balanced the panel perfectly. So if you've ever wondered how the neutral needs to know what the imbalance should be, or how does this connection know whether or not it's going to carry an imbalance, it has to do with the voltage difference between this point and this point. And what controls the voltage difference is when you have an imbalance, you create not 120 here, you can create other voltages there for a difference in potential. All right, cool. Hopefully that helps some people. I feel like I'm going to have to come at this a few different ways to get the idea across to the people who are curious. But if you wanted to investigate a diagram or an exercise that demonstrates the same idea, it's called a Wheatstone bridge. But yeah, all right, that's how the neutral carries the imbalance and how the voltage plays into it and how the neutral knows whether or not there's going to be an imbalance to carry. All right, thank you very much.